Okay, let me start out with expressing the deepest gratitude on behalf of all of my co-authors for receiving that great Charles Hatchett Award 2015 for our paper, Development of High Chromium Ferritic Steels Strengthened by Intrametallic Phases. Before I start into my presentation, I'm going to give you a short outlook on the upcoming contents. I will start out with a short motivation section on worldwide energy demand, the specific needs of the German Energiewende and what this means for future material selection and development. And I'm going to give a short introduction on steam oxidation resistance and creep strength of state-of-the-art ferritic martensitic steels. The main part will be on our high chromium ferritic steels strengthened by intrametallic phases. I'm going to give you some information on the alloying philosophy, the effective strengthening mechanisms. I'm going to talk on the specific role of niobium for thermomechanical treatment, microstructure, mechanical properties of our so-called hyperfer steels, which means high-performance ferritic steels, which is a further development of the steels that we described in the award-winning paper. And in the end, I'm going to conclude my talk. I'm going to give you a short outlook on the future perspectives, our development goals, and the partners we are working with right now. So whatever projection on worldwide electric energy demand you look, what they all have in common is that until 2030, they predict a rise in international energy demand of about 50% until year 2030. And that means that if we want to go for resource protection or mitigation of emissions, we have to reach some improvement in generation efficiency. And this is only possible by a rise in the operation parameters of thermal power plants. And for this, we need new and improved materials. Furthermore, the German Energiewende, which originally meant the turn away from nuclear power generation and in the future will mean the turn away from fossil sources of energy towards regenerative power sources, will pose a strongly increased requirement in the amount of required control energy, because in 2013 we already had about 40 gigawatts of installed intermittent solar and wind power. And that means that load flexibility in combination with further increased efficiency is already needed right now for the backing thermal power plants. This means enhanced thermal cycling capability will be needed in the future. We will have more frequent startup and shutdown cycles and longer and more frequent downtimes. And to summarize this, in my opinion, the processes will remain, but the operation parameters will significantly tighten. And that means for sure new challenges for plant maintenance, design, and especially for the design of future materials. So let me give you a short introduction on the steam oxidation and creep strength properties of state-of-the-art 9 to 12 chromium ferritic martensitic steels. And you can see them here lined up as a function of their chromium content, starting out with P92 as a 9 chromium steel, going up with higher chromium content to VM12 and X20, which are 12 chromium steels. And you can see the oxidation rate, which is represented by the black line, decreases with increasing chromium content. In turn, that means that steam oxidation resistance rises with rising chromium content. But unfortunately, on the other hand, what is represented by the red columns, the creep strength of these materials, the other way around, drops with rising chromium content. As we want to go up to higher temperatures of about 650 degrees C, you see that if you want to maintain sufficient steam oxidation resistance, you have to go up in chromium content. And this even sharpens the problem with the drop in creep strength with rising chromium content. And that is, for example, for Z-phase formation and delta ferrite formation, which troubles you with complete martensitic transformation upon cooling, and that leads to the drop in long-term creep strength. So to summarize this, in case of the state-of-the-art creep strength enhanced ferritic martensitic 9 to 12 chromium steels, creep strength and steam oxidation resistance together seems to be an antagonism, and that is one of the main reasons why most, or let's say all, the efforts in creating new high-strength, sufficiently steam oxidation resistant 9 to 12 chromium steels failed during the last 20 years. So having a look at the material classes that are available for power plant application, for structural application in thermal power generation. The most important material class today is the ferritic martensitic steels I've been introducing to you. Furthermore, we do have austenitic steels and high-performance nickel-based alloys. And in the motivation part, in the very beginning, I've been talking about cyclic power plant operation. And if we now rank these material classes by material properties which are crucial to cyclic operation, you first have to mention TMF, what means thermomechanical fatigue resistance. And to be very honest, even if the ferritic martensitic steels are or let's say the most important material class today, there is not a lot known about thermomechanical fatigue resistance of these materials. All the ferritic martensitic materials are right now clearly limited by their high temperature oxidation and corrosion issues because of the relatively low chromium contents of about 12%. Creep is a property which is okay because they have been designed for that. Technology means all the issues which are touched by production of semi-finished products, of components, and the construction and erection of whole power plants. This is not a problem because the materials are state-of-the-art, and cost is not a real issue because these are the benchmarking materials. If we now look into alternative materials like the austenitic and the nickel-based alloys, the picture is a little bit reversed, it's a little bit different. Typically, their thermomechanical fatigue resistance is considered to be worse because their thermal expansion coefficients are much higher and their heat conductivities are lower. Oxidation, corrosion issues, downtime corrosion issues should not be a problem because most of these grades feature chromium contents higher than 15% or even 20% in case of the nickel-based alloys. Creep resistance is not a problem too because these materials are stronger. Technological issues are, let's say, more or less solved because a lot of money has been invested, especially in the nickel-based field during the last 10 to 15 years. But for sure, what is a problem today and will remain a problem, is the higher cost that is implied by the use of austenitic steels and especially high-performance nickel-based alloys because the nickel contents are especially in case of the nickel-based alloys, higher than 50%, which leads to exaggerating costs. So the question is, there is a fourth material class, the ferritic steels. These steels traditionally are not regarded for structural application in high-temperature power generation. And that is for the reason that this material class is typically considered to be not creep strong enough. But what is for sure is that corrosion issues should not be a problem because the ferritic stainless steels mostly do feature chromium contents higher than 15%, which would be enough. And cost should be another advantage because they will not be much more expensive than the ferritic 9 to 12 chromium steels. But if you have a look into the ferritics column, you see that a lot of question marks gather in this column, and the question is, could such a material based on a fully ferritic steel can be an alternative? And because there are such a lot of question marks, our decision just was, for sure, this is interesting for science. So let's see if this can be interesting for practical application too. So and this was the starting point of materials development, the starting point of the development of a fully ferritic, high chromium stainless steel. You start out with an iron base, you put into some solid solution strengtheners like chromium, tungsten, and niobium. So to be frankly speaking, chromium was included for corrosion resistance, for steam oxidation resistance, and the solid solution strengthening mainly stems from tungsten and niobium. So this solid solution strengthening gives a boost in the creep strength of the matrix, but this is still not enough. So we'll go further for precipitation strengthening. You put into some more tungsten, some more niobium, a little bit of silicon. You restrict the nitrogen and carbon contents to very low levels to force the precipitation of a mixed lavas phase. The composition is given up there on the slide. And now I have to point out that our materials are completely ferritic at any temperature, so they do not undergo martensitic transformation upon cooling. And that means that if you want to go for enhanced dislocation strengthening, like it is done in the martensitic steels just by the martensitic transformation, you have to go for specialized thermomechanical treatment. And this gives another great leap in creep strength, but for sure, like it always is in high temperature materials, if this boost in creep strength is really stable, is a question of microstructure stability in the long term. So traditionally or historically, our steel development dates back to the development of the commercial grade Crofia 22H, which is a 22 chromium ferritic stainless steel, which was designed at our institute together with VDM Metals in Germany. And originally this grade was developed for the application in high temperature solid oxide fuel cells for a temperature range of about 700 to 900 degrees C. And in the course of this alloy development, approximately 45 trial alloys have been produced. And some of these trial alloys featured fluctuations in chemical composition or changes in chemical composition, like for example a lowered chromium content, like in the low chromium alloy, differences in tungsten content for the zero titanium alloys, like they are named right here on the slide, differences in niobium content, fluctuations in silicon content, and changes in titanium content. And the mechanical properties of these trial alloys showed very promising results, for example, for creep strength at lower temperatures in the range of 600 to 650 degrees C2, and this is what we described in the award-winning paper. So what is the specific role of niobium in these alloys? To give an answer to this, we have to have a look into some simplified phase diagrams, but I'm not going very deeply into detail. So to keep it simple, if you want to go for strengthening a fully ferritic steel by intermetallic phases, and if you just want to do it by simple tungsten alloying, you have to go up to a tungsten content of approximately 7 weight percent to reach sufficient creep strength or reasonable creep strength. And that means that such an alloy would be, on the one hand, very expensive. On the other hand, it will be hard to process. And if you think about weldability, such a high tungsten alloy should be a nightmare. If you go, on the other hand, for combined alloying with niobium, like it is shown on the right-hand side, you see that very small amounts of niobium are already sufficient to really reach reasonable creep strength in these materials. And this is for the formation of this mixed lavas phase that I already mentioned some slides ago. So frankly speaking, and to keep it simple, niobium replaces tungsten. It is incorporated into the lavas phase and refines it. It forms smaller particles. Furthermore, it boosts precipitation kinetics of the lavas phase. It forces a so-called high-temperature lavas phase with a higher dissolution temperature. That can be seen on the right phase diagram. It is represented by the blue curve. The dissolution temperature is somewhere close to 970 degrees C. In comparison to the lavas phase in the 7 tungsten alloy, which dissolutes at approximately 670 degrees C, the lavas phase in the combined alloying material should have much better long-term stability. And what is beneficial too, if you go for niobium alloying, you do not form the G phase. You can see the G phase is represented by the red curve on the left-hand side, and you see that in the application temperature range of approximately 600 to 650 degrees C, you do have a very steep phase change from the lavas phase to the G phase. And this is what you really don't want to have if you think about cyclic application, where you do have temperature fluctuations quite frequently. So if we now change, or let's say in this case, increase the niobium content, it rises the volume fraction of the lavas phase. This is shown in these 2 micrographs. So these are micrographs taken from 650 degrees C annealing after 3 hours. The upper picture is from one of our new trial alloys with 17% in chromium. a specific tungsten content and a single niobium content. The lower picture is from an alloy which is quite similar considering the chromium content and the tungsten content. The only difference is that the niobium content is doubled. And what you can quite nicely see is that the alloy with the higher niobium content forms much smaller particles, which is reflected in the particle diameter that you can see as a function of time in the diagram. So the blue curve is for the single niobium alloying, the red curve is for double niobium content, and you see the particles are much smaller, and obviously in the long term, up to 1,000 hours right now, the higher niobium content seems to be beneficial for stabilization of the particles, what can be quite nicely seen in that micrographs that were taken after 1,000 hours. Double the niobium content leads to less coarsening of the particles, and that is very beneficial for long-term application of such alloys. Furthermore, doubling or increasing the niobium content does not only have a direct impact on application, it does have a direct impact on processing too, and this is depicted here in that graph. Again, the color code is the same. Blue is the base composition, red is the composition with doubled niobium content, and you can see that on the high temperature end, the dissolution temperature shifts by approximately 100 degrees C, and this does not only lead to higher long-term stability, this for sure means we have to change the process if you go for rolling or forging of these materials. So now coming to the properties, starting out with mechanical properties, the tensile strength. As I already pointed out, our materials are fully ferritic. We do not have martensitic transformation, and that's the reason why we do only reach moderate tensile properties in comparison to a 9 chrome steel, here grade 9-2, which is represented by the green curve, the green triangles. The filled blue stars represent a composition, a chemical composition quite close to the commercial Crowford 22H alloy, and you can see it's far below, but this is not really a problem because we can alter the tensile properties just by processing, and this is what I'm going to demonstrate to you in the following. At first, we'll have a look into creep strength, this time for 600 degrees C. So there are 3 groups of alloys. It's first the Crowford 22-like specification, which features a chromium content of 22 weight percent, a tungsten content of 2%, and a niobium content of approximately 0.5%. There is a group of alloys with higher tungsten and niobium contents, and the low chromium version, which has the same tungsten and niobium content than the Crowford 22H specification. This alloy just features a lower chromium content of about 18 weight percent. If we compare the creep performance of these materials, of these trial alloys to ferritic martensitic grades to benchmark this, we will see that at a high stress level of about 145 MPa, the higher tungsten and niobium alloys are competitive to the 9 chrome grade TP92, which is the benchmark today in power plant application. At an intermediate stress level of about 120 MPa, the baseline composition, the Crowford 22 composition, is still competitive to the most steam oxidation 12 chromium ferritic martensitic steel VM12, and the higher tungsten and niobium content materials perform much better. What is a very interesting and important finding in this circumstance is that the reduction to 18% in chromium does not have negative implications on creep strength. So just compare the creep performance of the original Crowford 22H specification and the low chromium, the 18 chromium version. You see that there's not a big difference, and this is really an interesting finding which was documented in the award-winning paper. Some words to microstructure and particle stability. The micrograph you can see here was taken after comparatively short time annealing of 100 hours at 600 degrees C from the 2.5 tungsten alloy. And you see a multitude of very small particles, and the graph beneath it shows that the growth of these particles is quite rapidly during the first 1,000 hours, but in the long term, these particles coarsen very slowly, which is quite nicely depicted in the micrograph taken after approximately 26,000 hours on the upper right. So the particles are really stable. Some more words on secondary phase formation. Always when you're talking about ferritic high chromium stainless steels, you always have to deal with the sigma phase, and this phase is very undesirable because it segregates preferentially to grain boundaries. And if it forms continuous films at the grain boundaries, it might deteriorate the ductility in the long term, which is very undesirable. Unfortunately, the sigma phase forms in all the 22 chromium alloys, like you see it in the micrograph. But, and this is very beneficial, the cutback in chromium content to 18 weight% helped a lot to mitigate formation of the iron chromium sigma phase. And like I demonstrated to you some slides ago, this does not have negative impact on creep strength, but the question remains, what about steam oxidation resistance if we cut back the chromium content? And this is what you can see here. So here this diagram depicts weight changes or weight gains during annealing in simulated steam environment. Temperature is 600 degrees C. You see on the upper end you do have the performance of the 9 chromium martensitic steels, approximately an order of magnitude lower the performance of the 12 chromium steels, and approximately another order of magnitude lower at the lower end of the 12 chromium martensitic steels. We do have the weight gain rates of our high chromium ferritic steels, which is mostly comparable to high chromium austenitic grades. And what is really nicely depicted here is the comparison of the green 18 chromium curve and the red 22 chromium curve. You see that they more or less are on the same level, and that means that the cutback in chromium content to 18 weight% does not negatively affect steam oxidation resistance, which was one of the basic findings in the award-winning paper. So as a preliminary conclusion, we can state that ferritic steels, which are strengthened by intermetallic phase particles, offer promising creep strength and favorable steam oxidation resistance in combination, which is a quite unique thing. But there remain questions beyond. So first question for sure is, what is the further potential in compositional changes? What is the role of thermomechanical controlled processing? And what properties relevant to application can be reached with that? And this is what we concentrated on during the last approximately 2.5 years. So coming back to tensile strength, again, doing the benchmarking against the martensitic grade 92, you can see here that by changing the hot rolling parameters, the yield strength of our high chromium ferritic steels can even be tuned beyond the ultimate tensile strengths of ferritic martensitic grades. And this can be done over the whole temperature range with still sufficient and reasonable ductility. And the takeaway message is the tensile properties we can reach in our fully ferritic grades are comparable to ferritic martensitic grades. Processing, thermomechanical controlled rolling, does not only affect short-term tensile properties. It has a strong impact on particle microstructure, and for this reason for creep performance too. What you see here is a creep curve from 120 MPa creep experiment performed at 600 degrees C, and rupture appeared after only 106 hours. So frankly speaking, this is not really a creep curve. But if you do the same experiment with a moderately hot rolled material of the same chemical composition, you can see in that micrograph below in the red box, the number of particles is much higher than in the solution treated state. The particles are much smaller, and this has a very decent impact on the creep properties. You see that the shape of the creep curve changed quite a lot, and rupture appeared after approximately 30,000 hours. So a thermomechanical treatment state has an enormous effect on creep strength and particle microstructure. This means, on the one hand, that we do have great freedom to adjust property profiles, but on the other hand, this means that such materials will for sure be more complex in development and processing than the materials that we have today. So, coming back to that representation of what we did in the past, taking all this knowledge on alloying and processing together, we right now try to transfer this into a new material class, which is called the high-performance ferrite materials, and we're going to optimize this for steam power plant application in a temperature range of 550 to 650 degrees C, or maybe even for the application in petrochemical plants where higher corrosion resistance is needed. So, to achieve this, we produced a couple of new trial alloys. Some of them are depicted here. This, again, is a stress rupture diagram, so we're talking about creep resistance again, this time at 650 degrees C. And as I already pointed out, we produced a couple of new trial alloys. The nominal chemical composition is given in the table at the right-hand side. So all of these trial alloys feature a further reduced chromium content of about 17%, combined with enhanced tungsten and niobium content for increased lavas phase formation, and optimized rolling parameters, and for this reason yield creep strength, which is already far beyond the ferritic martensitic grade 92. And this is achievable without sigma phase embrittlement. This makes us very proud. But most of the very interesting long-term low-stress experiments are still running, are still in progress. So I've been talking about thermomechanical treatment quite a lot, being aware of the fact that this is not very desirable to first invest a lot of effort in tuning a microstructure by your processing, and then later on maybe destroyed by welding. So we had a look into heat treatment too. This was done, for example, with a batch taken from our newest productions, and we tested it in the hot rolled state. So you have a creep curve, the black one in the diagram that represents the creep performance of the hot rolled state, and the red and the orange curve represent the creep behavior of the same batch of the same material after solution treatment and a high temperature heat treatment added to it. That's the red curve, and a low temperature heat treatment, that's the orange curve. And you can see that both of these solution annealed and heat treated materials approximately reach the same creep rupture strength than the hot rolled material, and that means that creep strength can be regained from the solution treated state by simple heat treatment, and this is very beneficial. Furthermore, these heat treatments are very effective in homogenizing the hardness profiles after welding, and they do not harm the creep strength of the hot rolled material. So, and this really opens up the gate to application, for example, in the solution treated state where you don't have to go for thermomechanical processing. So the takeaway message is thermomechanical processing is not mandatory, but it can be very beneficial if you want to go for very high strength application. For sure, this is still subject to further optimization, so we're far away from being finished with that. In the motivation part, I've been talking about thermomechanical fatigue resistance for cyclic power plant operation. And that is why I brought some data on thermomechanical fatigue. What is done in a thermomechanical fatigue test is you just take a specimen, cycle it through a given temperature range, in this case from 50 to 650 degrees C, employing quite steep heating and cooling temperatures, in this case 10 Kelvin per second. You do not go for holding times at the minimum and maximum temperatures because you want to restrict creep as far as possible. And in this case, it's a so-called out-of-phase thermomechanical cycle, and that means that the testing machine obstructs the thermal expansion of the material completely. And then you see the performance of 3 different material classes. Red is a ferritic martensitic grade, again T92, the most creep-resistant material that is available today. You see it reaches a very high stress range in the initial state. This is because of excess dislocation density from martensitic transformation. But this recovers quite rapidly during the first, let's say, 50 cycles before the material enters a stable phase, and after approximately 1500 hours, damage and failure comes quite rapidly, so the material is comparatively unforgiving. In case of the austenitic grade, here alloy 316, that's represented by the green curve. You see that this material performs completely different. You do have pronounced hardening in the initial phase. You again enter a stable phase, and after approximately 1300 hours, damage comes rapidly too. So obviously this material seems to be unforgiving too. And the blue curve represents our new ferritic hyperfer 17 chromium 2,4 grade. And this one reaches higher lifetime in combination with higher stress range than, for example, the ferritic martensitic grade. And it seems to have more decent failure behavior, which is quite positive. And the microstructural reason for this behavior is the following. So if you take into account the ferritic martensitic steels, you can see in the virgin condition this well-defined martensitic microstructure, and in the fatigue condition depicted below, you see that this microstructure is completely lost. Ferritic martensitic steels suffer pronounced recrystallization in severe thermomechanical fatigue loading, which then later on causes premature failure. In case of the austenitic steel, such recrystallization does not occur. The grain structure is completely stable over the whole range. The premature failure is more or less owed to the comparatively high thermal expansion coefficient of these materials, and that means that the amount of plastic strain energy per cycle is much higher than for the ferritic martensitic and the ferritic steel. In case of the ferritic materials, microstructure remains stable too, so we don't suffer any recrystallization. And to summarize this, we can say that our hyperfer ferritic steels combine microstructural stability, low thermal expansion, and high heat conductivity, and this is very beneficial. And for this reason, they reach the longest lifetime in thermomechanical fatigue loading. So the last thing I'm going to talk about is impact strength. This is a property which is mostly demanded by design codes, which have to be taken into account in power plant construction. And like you can see here, the ductile to brittle transition temperature of our hyperfer steels in the solution annealed state is not very beneficial. It's well beyond 100 degrees C, namely 135 degrees C, and this is not very desirable. Nobody will listen to you. But we were able to prove that by simple heat treatment, a ductile to brittle transition temperature shift of approximately minus 70 degrees C can be achieved. So in a solution annealed and heat-treated state, the ductile to brittle transition temperature is approximately at 65 degrees C, and we already found out that with combined alloying, we can further decrease this. We're able to increase the lower shelf energy, and we're very positive that we are able to stick to the European regulations. So for sure, this is another topic which is still subject to further optimization, and right now we're about to implement this heat treatment into our lab scale production. So what do we want to go for in the future? What are our desired future applications for the high performance ferrite family? So first, for sure, there is applications where ease of processing, weldability, and impact strength play a major role. For example, thin wall components like tubes or sheets. This is what we want to develop or further develop the hyperfer grades for. These would be alloys which will be applied in the solution annealed state. That means we have to go for changes in chemical composition to increase creep strength. And on the other hand, we're going to further develop another spin-off of the high-performance ferrite family, the so-called hyperforge materials. These will be great with an optimized thermomechanical processing for applications where weldability does not play a role, but, for example, increased short-term or low-temperature tensile properties are beneficial, like, for example, in blading application, or where good stress relaxation properties are desired, for example, for bolting application. So, and for this reason, we produced a couple of new trial melts with approximately double Laver's phase content of about 7 volume%. For this reason, these materials will have enhanced mechanical and further improved impact strength properties. And we're going to further decrease the stability range of the undesired iron chromium sigma phase to temperatures of approximately below 550 degrees C. Together with our partners from the Oak Ridge National Labs in the USA and voestalpine Böhler Welding, first matching shielded metal arc welding electrodes were developed, and first small and thick welds were produced. And concerning the optimization of the hyperfur trial steels, we're working on optimized hot rolling and forging parameters. We're looking a little bit more into heat treatment alone. And this work is done again in cooperation with Oak Ridge National in the USA and partners at the Technical University of Aachen in Germany. So for us, this means there is a lot of characterization work to come in the future, which I'm really looking forward for, because this is a very rewarding job, putting things into effect that came from your idea and later on see that it works. So in the end, there's nothing else to say for me than thank you to the colleagues at Forschungszentrum Jülich, because such a development cannot be achieved by one person alone. The list is quite long. Some of the colleagues already left for retirement. Others went for other jobs. I want to particularly mention the colleagues at Oak Ridge National, namely Yukinori Yamamoto, Ying Yang, and Pete Tortorelli. I want to mention the colleagues at voestalpine Böhler Welding in Germany, in Hamm, Martin Schmitz-Nieder and Olena Trunova, and the colleagues at the Technical University of Aachen, namely the Institute of Ferrous Metallurgy, Mr. Dickert, who now left for an industry job, Mr. Schulte, Mr. Stieben, Professor Black, and Mr. Hessling. And in the end, thank you very much for your kind attention.